Today we are doing integration by parts. This is an awesome integration technique. I love teaching this lesson. I think it's one that this is a technique that kids usually like quite a bit when it comes to integration. Alrighty, this technique was developed by the English mathematician Brooke Taylor. Brooke Taylor is also responsible for Taylor's series in polynomials. That's what we're going to be doing in our last new unit of the year, Unit 12. This technique is useful when the integrand is a product of an algebraic and a transcendental function, like 3x to the fourth times sine of 3x. 3x to the fourth is algebraic. Sine is one of our transcendental functions. You guys, a transcendental function is a function that cannot be written without an additional function. So I think of it as only x's. Okay? Transcendentals include all of the trig, the exponential, the logarithmic, and the inverse trig functions. Alrighty, those are all the transcendental. So 3x to the fourth is algebraic. Sine is transcendental. So 7x squared, e to the 3x. X, ln a natural log, ln of 3x. It's also useful when you have a product of different transcendental functions. E to the x at times sine. Two transcendentals, sine and a log, exponential and a log. You can use it when you have any product, okay? It can be used. The question is, should you use it? Okay? A tip that I have for you that I need to add to this actually. A tip that I have for you is to make sure the argument in the transcendental function, make sure the argument is linear. We need for the argument to be linear, all right? So log of 3x, 3x is linear. E to the 3x, the argument there is linear. Here's another 3x, the argument is linear. Here's another 3x. Here's a 2x, the argument is linear, 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 linear. They're all linear arguments, okay? If it is a power, you guys, it's a high likelihood that you're going to use a regular U sub and not by parts, okay? So make sure the argument is linear. So I think product and linear argument. Product and linear argument. Okay? That's when you use by parts integration. I'm going to do a quick derivation to get our formula that we use for by parts integration. I'm going to show you how the formula comes about by taking the derivative of a product. These are all products, right? So I'm going to take a derivative of a product. I'm going to call the two functions u and v. Both of these are functions with x's in them, all right? I'm just calling them u and v rather than f and g, all right? We know to take the derivative of a product, we use the product rule. U prime v plus v prime u, right? But I'm going to write those derivatives, instead of using prime notation, I'm going to use Leibniz's d notation. Du dx times v plus dv dx times u. Little product rule there. Now what I'm going to do is I'm just going to move this term to the other side. So I'm going to have that minus du dx times v is equal to dv dx times u. Okay? At this point, I'm going to take the integral of both sides. I'm going to take the integral of both sides with respect to x. integral of both sides with respect to x. Alrighty? So when we're integrating both sides here, since these are two different terms separated by a subtraction sign, I'm just going to take the the integral of both pieces individually. So I'm thinking of this as, don't necessarily have to rewrite this, the integral of that minus that integral, and that's going to equal this integral. I'm just going to rewrite this one. Okay, so for this first piece right here, our first piece, I think of it as the dx's are canceling out, and I'm left with the integral of the derivative of uv. The integral of the derivative of uv, those cancel each other out. The integral and the derivative cancel each other out. We're left with just uv. Over here, the dx, I think of it as canceling out, Leibniz's wonderful fractional notation there, minus the integral. We still have du times v, right? I'm going to write that as v du in that integrand. And this is equal to these dx's, and then we have the integral of u dv. Now all I'm going to do is to change sides. So I'm going to write this in the front and this in the back. So integral u dv is equal to uv minus the integral of v du. That is our formula for biparts integration. Okay? Alrighty, let's do some examples. Now that we know a formula for it, let's do some examples. We're starting with this one. Okay? So this integral is this integral, you guys. So I'm going to assign something here to be my u, and everything else will be part of my dv. Okay? I'm going to do this using a tabular method. I find that kids are highly successful doing biparts integration using a table method, tabular method. So I'm going to create a table for my u and my dv. All right? Okay? So I'm going to, so the question is what to let u be. What should we let u be? And I created this little rule for what to let u be. If there's a log, then you let that be your u. If there's no log, but there is an inverse trig function, let that be your u. If there's no log or inverse trig function, but there is an algebraic function, let that be your u. And in this case, we don't have a log or an inverse trig function, but we do have an algebraic function. I will let that be my u. So my dv is everything else. Continuing with this though, you guys, if there's no log and no inverse trig function and no algebraic function, you're left with these two, right? These two can actually be switched. You can do exponential first and then trig, or trig then exponential. I'm sorry, yeah. But these last two don't really matter. Those can be switched. I prefer exponentials for my u, but if you did trigs, that would be fine as well. Okay, so we got our u and our dv. Now let's think of our formula here. We want u times v. We don't have v. We have dv, right? So I need to integrate this side. I need to, and over here, then I'll have v here. I need du. I need to find the derivative of this side. So we take the derivative of u and we take the integral of dv. All right? So I'm going to take the derivative of u and the integral of dv. Now, the beauty of the table method is this. what we can do here is I'm going to show you a way that we don't have to end up with the integral here. I'm going to do one more step. I'm going to get to 0. Here's the thing, you want to take the derivative and keep taking derivatives until you get down to 0, if possible. So if this is algebraic, x squared, x cubed, x to the fourth, you're going to be able to get down to 0, right? So keep taking the derivative, if possible, till you get down to 0. And then you line up, you keep taking integrals until you line up with that line. Okay, so 3 here, 3 here. Now, we need u times v. There's u, there's our first v, right? So our first term of our answer is going to be x e to the x. Okay? Then we need a minus. So we need a minus over here. So here's the way I think of it, you guys. We start plus and then we go minus. If it continued, I know we have a 0 here, but if it continued, we would do plus, minus, plus, minus. That allows us, you guys, this tabular method allows us to do several steps of a bipart, several iterations of a bipart process, all in one table. Okay? So we go from here to here. After you do the plus, minus, you multiply diagonally and multiply diagonally. So our next term here of our answer would be a negative e to the x. Now, we have a 0 here, but sometimes you won't have a 0 there. If you go horizontally, you integrate because you're going to still have an integral there. Okay? So if you do go horizontally, if it's not a 0, think of it as, in this case, we can think of it as plus the integral of 0 times e to the x. But 0 times e to the x is 0, and the integral of 0 is 0. So this is just 0 here. But sometimes it won't be. We'll do somewhere it's not. So all we do is add c, and we're done. All right? So our answer here is x e to the x minus e to the x plus c. That's the integral. Let's do another one. So u and v, we know it's by parts because it's a product and the argument is linear. It's a product of functions and the argument is linear. So u and dv, algebraic, no logs, no inverse trig, but algebraic. So 2x and dv is everything else. We take the derivative until we get down to 0. We take the integral till we line up with the 0. The integral of sine of 3x. When you're integrating sine, change the sign. It's going to be 1/3 cosine of 3x. I think of it as this, you guys. If you were taking the derivative, it would be a times 3. We're not taking the derivative, we're taking the antiderivative. So instead of multiplying by 3, we divide by 3. Okay? By the way, don't put a plus c. Don't put a plus c. It's going to muddy things up and it would cancel anyway. So don't put a plus c in your table. Save your plus c for the end. Okay, so the antiderivative of this piece now. When you're integrating cosine, keep the sign. So we'll have negative 1/9 sine of 3x. Okay, plus, minus, plus, multiply diagonally, integrate horizontally. So our answer is going to be negative 2/3 x cosine 3x plus 2/9 sine of 3x. That's 0, so plus c. And we're done. These get very quick. All right, next up. Okay, algebraic, transcendental, the argument is linear, so by parts. No log, no inverse trig, but an algebraic, so 4x cubed is our u. dv is everything else. We take the derivative until we get down to 0. So 12x squared, 24x, 24, and 0. We take the integral until we line up with the 0. So integrating sine, change the sign, 1/2 cosine of 2x. Integrating cosine, keep the sign, 1/4 sine of 2x. Integrating sine, change the sign, 1/8 cosine 2x. Integrating cosine, keep the sign, 1/16 sine of 2x. Plus, minus, plus, minus, plus. Multiply diagonally. Integrate horizontally. So our answer is, let's see, negative 2x cubed cosine of 2x, positive plus 3x squared sine of 2x, plus 3x cosine of 2x, minus 24/16, so 3/2 sine of 2x. The integral is going to be 0, so plus c, and we're done. You can notice the pattern of the decreasing powers of x's, of the alternating between cosine and sine. We started with sine, so we start with cosine. You can notice these patterns going on. Alrighty, next up, number 5. X squared ln x. Algebraic, transcendental, linear argument, so by parts, u and dv. This time we have an ln. We have a log, so that's going to be our u. dv is everything else. Okay? When we integrate ln of x, when we take the derivative of ln of x, we get 1 over x. If we took the derivative again, and kept taking derivatives, would we ever get down to 0? No, we would never get down to 0. So stop. Pause right here. Pause here and see what happens. I'm taking the integral of x squared. The antiderivative of x squared is 1/3 x cubed. Plus, minus. Multiply diagonally. Integrate horizontally. This time we're going to have an integral, right? So we have 1/3 x cubed ln x minus the integral of the product. The product is 1/3 x squared, which we know how to integrate. Now, so when you're done with that step, you guys, this right here, chances are you won't do by parts on that step. Okay? So we have a minus 1/9 x cubed plus c. And we're done. Next up, integral of an ln of x. So at first glance, this does not look like a by parts candidate. because this does not look like a product. However, it is a biparts candidate. We can always force it to be a biparts problem. You can think of this as 1 dx, all right? So we are going to treat this, force it to be biparts. Remember, you guys, anything we could try to do by any integral, we can try to do biparts on it. It's just that some are better candidates than others, okay? All right, we have an ln, so that's our u, ln of x. dv is everything else, so dv is dx. The derivative of ln of x is 1. The integral of dx is x. Plus, minus, multiply diagonally, integrate horizontally. So we get x ln x minus the integral of the product, 1 dx. X ln x minus x plus c. The integral of ln of x dx is x ln x minus x plus c. That is the last integral that I have on our formula sheet, you guys. Our sheet of formulas to memorize. That's the last integral to memorize. Now, what if you don't memorize it? If you don't memorize it, just remember that it came from biparts. Okay? It's a pretty quick biparts problem. All right? So I'm not saying that you have to memorize it. The reason I ask students to memorize it is because many times students will see this and not know to do biparts on it. Okay? Because it doesn't look like the typical biparts problem. But I ask my students to memorize it. X ln x minus x plus c. X ln x minus x plus c. It has almost like a rhythm, a beat. X ln x minus x plus c. There are 3 times we say x, right? X, and oftentimes I just say log instead of ln. I say log. X log x minus x plus c. And it has even better like rhythm. X log x minus x plus c. Alrighty? In class, I would have you guys repeat that several times. Okay. Integral of arctan of x. Okay, again, just like with this one, it doesn't appear to be a biparts candidate, but we can force it to be biparts. U dv. Okay? There's no log, but there is an inverse trig function, so that is our u. Okay? dv is everything else. The derivative of arctan of x is 1 over x squared plus 1. Just like with ln, if we kept taking derivatives, we would never get down to 0, so stop, just pause. The integral of dx is x. Plus, minus, multiply diagonally, integrate horizontally. So we get x arctan x minus the integral of x times x squared, x times 1 over x squared plus 1. So x over x squared plus 1 dx. So for this, we need to do a little, so again, when you get to this integral, just integrate like we always have. We've had this exact problem before in the past, before biparts. This is likely not going to be a biparts problem if you did it. Oh, I shouldn't say that. Maybe it is. But we just go back to the drawing board. What do we do on this? I'm going to u sub the bottom. U sub the bottom. U is x squared plus 1. du is 2x dx, 1/2 du is x dx. That is up on top here, so 1/2 du goes in for that. And I get x arctan x minus 1/2 du over u, and that's an ln. Remember, you guys, when you let u be the entire bottom, you are going for an ln. Okay? When you let u be the entire bottom, you're trying to get it to be an ln. When we complete the square in the bottom, we're trying to get it to be an arctan. Okay? So this is x arctan of x minus 1/2 ln absolute value of u plus c. This is one of those where this argument can never be negative. So as a multiple choice answer, I forgot my x there, they would replace the absolute values with parentheses to, quote, simplify it. Alrighty? Okay, let's do this one now. E to the x times cosine x. So we have two functions, an exponential and a trig. That is, let me go back to this little table. These are the last two. Those are the last two on here, right? You get a product of those two. We have to do something a little bit special, okay? We are going to use by parts, but we're going to do it a little bit special. So, u and dv. So, no log, no inverse trig, no exponential. So I'm going to let u be the e to the x. dv is everything else. We take the derivative of e to the x, and that is e to the x. Now, if I did what I've been doing, I would stop right there and do my multiplying and stuff. But I know these problems. I know what's going to happen in here, and I know that when you have an exponential times a trig like this, chances are you need to go one more step. One more step, okay? The integral of cosine, keep the sign. Integrate sine, change the sign. Plus, minus, plus. Multiply diagonally, integrate horizontally. So we get e to the x sine x plus e to the x cosine x minus the integral of the product e to the x cosine x. That is what we started with, right? That's what we started with. So that's why I went one more step, you guys. Because otherwise, if we stopped here, we would have e to the x sine x, and we would have to go do another table. We'd have to go do another by parts. Okay? So I wanted to get back what I started with. So let's think about what we have here. This is equal to this. So I'm going to write this as an equation. Integral of e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x minus the integral of e to the x cosine x dx. This is an equation. I'm going to get these two like terms together. I'm going to add this one to the other side, and now there will be two of them. This is a good spot to add my plus c, because I have an integral equals, so plus c. And now, divide by 2. Divide both sides by 2. I'm going to write that as a 1/2. I might even, since both of these have an e to the x, I might even factor out that e to the x and make it look like this. That's probably how a multiple choice answer would look. Okay? Now, By parts is definitely on the AP exam. Definitely. All right? I have totally seen these types of problems on the AP exam. I've seen that type of problem. I've seen that type of problem on the AP exam. Okay? However, this type, the type where you end up with the same thing that you started with, and you have to write the equation and everything, this particular type is not covered on the AP exam. But I know Calc 3 professors in general assume that you have seen that type of by parts problem. So that's why it is fair game for my unit test, and it is definitely fair game for the integration bee. All right. Next up, number 9. Where are we on time? 30 minutes. Yeah, this is going to be a little bit long. Okay. The graph of f is shown. Let's evaluate this integral. All right, f notation. The first thing you do when you see f notation is make sure that this is a plane, that the argument is a plane x. A plane x. Not 2x, not x squared, not x plus 1, a plane x. Once it's a plane x, then you're good to go to the next step. And I see by parts here because I see algebraic times another function. So I'm going to set up my u and dv table. I'm going to let u be the x squared. So dv is everything else. I'm going to take the derivative. This time I'm going to be able to get down to a 0, 2x, 2, and 0. I'm going to take the integral of dv until I get even with the 0. The antiderivative of f double prime is f prime. The antiderivative of f prime is f. The antiderivative of f is the antiderivative of f. We cannot do anything with that. So we just write it as the antiderivative of f. Okay? Plus, minus, plus, minus. We multiply diagonally. And we would integrate horizontally, but that is going to be a 0. So we're just going to multiply diagonally. So I'm going to have, and I know I have boundaries, so I'm going to apply the boundaries to the things that I can, and then for this integral, I'll put my boundaries back on. Okay? So we're going to have, I'm going to start with my brackets for my boundaries. So x squared f prime of x minus 2x f of x. My next one is going to be with the integral. So I'm going to close my bracket here, 3 to 5. And then I'm going to have plus 2 integral 3 to 5 of f of x dx. Okay? So right here, 5 goes in for x, minus 3 goes in for x. And then for this piece, the integral of f, I'm using the signed area under the curves, under f. Okay, 5 goes in for x, and I have 25 times f prime of 5. Well, f prime of 5, here I am at 5. F prime there is 1. The slope of the line tangent there is 1. Okay? Minus 2 times 5, which is 10. F of 5. F of 5 is negative 1. So that's what we get when we put 5 in for x. Now we subtract and we put 3 in for x. I'm going to have 9 times f prime of 3. Well, here we are at 3 right here. F prime is the slope of the line tangent. That will be 1 again. Okay. minus 2 times 3, which is 6, times f of 3. F of 3 is negative 3. So we put 5 in for x, then 3 in for x. Subtract those, right? Plus 2 times. Now here's our signed area between 3 and 5. 3 and 5. So here's 3 and 5, and I need that signed area, this signed area right there. Yeah? Well, it's below the x-axis, so it's negative. And the area there, I'm just going to count squares. 1, 2, 3, and a half, so 4. Negative 4. And this is an FRQ. We safe stop right there. If we have to do this for a multiple choice answer, then we would simplify, clean that up, of course. Number 10. Okay, given that f is twice differentiable with selected values of f and f prime given in the table, evaluate this integral. Okay, so once again, the first thing I would do when I see f notation is I look at its argument. That must be a plain x, and it is. So we're good to go. I'm going to do by parts because I have an f with f I have an x with f notation. So I'm going to do by parts again. So u and dv, I'm letting u be x. Oh gosh, you guys, I just realized something. I think when I made this problem, I thought that it was going to be, I'm sure I thought I was going to play, anyway. Let's change this. Let's change these boundaries. I'll change these on your worksheet. By the time you see this, it'll already be like that. Let's change this to 0 and, I don't care, 4. Let's change 0 and 2. All right. So x, 1 and 0. dv is f double prime of x. dx, the antiderivative is f prime. The antiderivative is f. And we do plus minus plus, multiply diagonally, integrate horizontally, but we get a 0 there, so that's always nice. So we're going to get here x f prime of x minus f of x evaluated from 0 to 2. Plug in 2. F prime of 2 is 4. F of 2 is 6. Minus 0 goes in for x. Well, when 0 goes in for this x, it's going to make that first term 0. Minus f of 0 is 2. Safe stop. If we had to clean it up, we clean it up. Number 11. So for number 11 here, I notice that my f notation does not have a plain x. So before I do by parts, before I do anything else, I need to take care of that. Okay? So I'm going to do a u sub. U is x squared. So this is going to be a u. Okay? du is 2x dx. 1/2 du is x dx, right? Okay, do I have an x? I do. I'm going to take one of the x's that are here and put it back in the back with my dx. So I'm going to have the integral of x squared f double prime of x squared times x dx. Now I'm going to do my u sub. In place of x dx, I'm putting 1/2 du. In place of x squared, I'm putting a u. So in place of this x squared, I'm putting a u. Now, what about our boundaries? We need our u boundaries. The top boundary was 2. The u boundary, when I do my u's, the u boundary will be a 4. Okay? The bottom boundary was 0, it's going to stay a 0. Then I'm going to have u f double prime of u du times 1/2. There's my 1/2. You could keep your 1/2 in with the u or leave it out, it doesn't matter. Now we can do by parts. So u and dv, our u is u, right? dv is everything else. Okay? Derivative with respect to u, derivative again, the antiderivative over here. So we get plus minus, yes? Multiply diagonally, integrate horizontally, and we get here, I'm going to have 1/2 times, okay, u times f prime of u minus f of u from 0 to 4. 4 goes in for u. 4 f prime of 4. F prime of 4 is 1. Minus f of 4. F of 4 is 7. 0 goes in for u. Well, when 0 goes in for this u, we just get 0 for that piece. Minus f of 0. F of 0 is 2. We safe stop, and we're done. So that's how you handle those types of problems with the F notation given a table or a graph.